Hi, I am trying to, there we go, get to the homework. Maybe. Finally, there we go. So the lab for this week is all about brightness and light gathering potential and the distance modulus. Read through this, try and work some of these problems, and then we're going to come down here to the problems. I'm going to show you over here how I solved the first problem of each type so that you can then try and solve the second ones on your own. So Rigel has an apparent magnitude of positive 0.14 and Deneb has an apparent magnitude of positive 1.26. What is the ratio of brightness of Rigel to Deneb? So, I made notes. The magnitude of Rigel, positive 0.14. The magnitude of Deneb, 0.16. The formula that we will use, brightness 1 over brightness 2 equals 100 to the 0.2 power, and then that is raised to the m2 minus m1. So the first thing we have to figure out is which star is m2 and which star is m1. And for these formulas, all the ones that we are talking about, m1 is always the brighter star. Remember, brighter means smaller number or a more negative number. So the smaller number, Rigel, is M1 and Deneb is M2. So what we're trying to do, brightness 1 over brightness 2, that's what we're looking for, the ratio, which is, what's the ratio of apparent brightness. And so to solve this in your calculator, you're going to use 100 and then x to the y 0.2. So that comes out to 2.5118864315095, which is not really, useful for us. So I'm going to shorten that down to 2.5118. So the brightness ratio equals 2.5118 to the 1.26 minus 0.14. So we solve this. So 2.5118 2 raised to the 1.12. So once again, 2.5118, and you use this x to the y key. So on all of these, when I'm showing you what actual buttons to push on your calculator, I put it in the circle. And so the brightness, 2.805, which means that the ratio of brightness of Rigel to Deneb is 2.805. So Rigel is 2.805 times brighter than Deneb. Move on down to the next problem. How many times brighter is the full moon at negative 12.5 than Venus at its brightest, negative 4.6? So the magnitude of the moon, negative 12.5, magnitude of Venus, negative 4.6. So which one of these is M1? M1 is the brighter one, and so the moon is M1, Venus is M2. Same formula, but we're going to use it differently this time. So the formula, brightness 1, brightness 2 equals 100 raised to the 0.2, and all of that is raised to m2 minus m1. So come over here, plus or minus, change this, the plus minus sign, negative 4.6 minus negative 12.5, which gives us a positive 7.9. So this ratio is 2.5118 raised to the 7.9, and so that comes out to 1,445. So the moon is 1,445 times brighter than Venus. If we look at these two and see, that basically there's 6 digits between negative 12.5 and negative 4.6. So 6 times brighter, 1,445 times brighter. This makes sense. We'll see that as we continue going. And so how many times brighter is Venus currently than at its brightest? We can come up here, and Venus at its brightest, negative 4.6. So you're going to have to go and look up how bright is Venus right now, which is pretty easy. You just type in current magnitude of Venus on a Google search and it will tell you. So there is that. Light gathering power. We're going to move on to the next type of problem because these two are identical to that one. Determine the ratio of the light gathering power of a 25 centimeter diameter telescope to the dark adapted unaided human eye. Assume that the pupil is 6.0 millimeters in diameter. So we come up here and light gathering power, that's the first time we see this formula. Light gathering power ratio from the telescope to the eye. So light gathering power of a 25 centimeter telescope divided by the light gathering power of the human eye. So a couple of things to remember. First of all, if we try to just plug in numbers, 25 centimeters, 2.0 millimeters, that doesn't work. Oh, in order to work this, we need to know that there is a relationship that the light gathering power is proportional to the distance, the diameter squared. Does not mean that it's equal. It means that it's proportional. So as the light gathering power of a telescope gets bigger, the diameter gets bigger. As the light gathering power of the human eye gets bigger, the diameter gets bigger. And we need to remember this squared. So now we go back here, type in the numbers 25 centimeters over 6.0 millimeters. This doesn't work because it all has to be in the same units. So we convert 25 centimeters to millimeters. Light gathering power of the telescope over light gathering power of the eye. So we have 250 millimeters divided by 6 millimeters, and all of that is squared. So 41.66, 250 divided by 6, 41.66, squared, 1,736. So, where's our question? Determine the ratio of the light gathering power of a 25 centimeter diameter telescope to the dark adapted unaided human eye. So 1,000, the telescope gathers 1,736 times more light than the eye. So we come out down here to the next question. What is the dimmest magnitude visible through a 25 centimeter telescope when viewing with a fully adapted human eye. Average human eye dilates to 6 millimeters when fully dark adapted and can see a positive 6 magnitude. So for this, and when we're looking at what is the dimmest magnitude, M2 equals M1 plus 2.5 times log 10 of the light gathering relationship is what we are looking for. We need to remember that, this relationship, light gathering relationship, is proportional to the diameter ratio relationship is proportional to the brightness relationship. So we can substitute these ratios in for each other. So B1 over B2 is just the 1,736 that we got from the previous problem, because we're still talking about a 25 centimeter telescope and a dark adapted unaided human eye. So M2 equals M1 plus 25 times the log 10 of this ratio. So which one of these is the brighter? Well, M1 is always our brightest, and if we're talking about the dimmest thing that can be seen through the unaided eye compared to the dimmest thing that can be seen with a telescope, the unaided eye is going to be brighter. So here's M1. So M2 equals 6.0 plus 2.5 times log 10 of 1736. So for most of you, the way your calculator is going to work is that you have to put in 1736 and then hit the log 10 button. If you hit log 10 1736, it's going to tell you error. So 1736 log 10 times 2.5 plus 6. And so the dimmest star that can be seen through a 25 centimeter telescope is 14.09. So problems 3 and 4 are worked just like these with different numbers. So that should be fairly easy to do. Magnitude and distance. How far away is Canopus, which has an apparent magnitude of negative 0.72 and an absolute magnitude of negative 3.1. So distance modulus. This is where we're finally beginning to look at how far away something is. We've been working toward this for 3 chapters. So the distance equals 10 to the power of apparent magnitude minus absolute magnitude plus 5 divided by 5, and that's in the units of parsecs. So, plus or minus 0.72 minus plus or minus 3.1 plus 5 gives us 7.38. So 7.38 divided by 5, and you can do this, 10 to the power, and then parentheses 7.38 minus 5. But, whichever way you want to do it works. And so 7.38 divided by 5 is 1.476. 10 to the 1.476 is 29.92, and then our units is parsecs. So problems 2 and 3 relate back to this, and we are, have a much simpler time with the color index. On this of the stars in table 2, list the ones that are more blue than the sun, less blue than the sun. So hopefully that helps with the math for these problems, because I only have one